Morning, my dear students. Myself, Dr.D.Raguraman, Assistant Professor, Department of Automobile Engineering and School of Mechanical Engineering, College Institute of Higher Education. This video class, we will see the topic, the limits, fixed tolerances. And the course code U18PCAU403, Design of Engine Components. Before going to see about the topics, limits, fixed and tolerances, as we are concerning with the subject concept is being what design of an engine components. While you are going for designing the engine components, especially engine components or what major engine parts you will be knowing. So on the major engine parts, there is cylinder, piston, as well as piston ring, connecting rod. Then it will be having a crank, and then a valve and a rocker arm. These are what main engine parts. So this engine parts, when you are going to make a design, you will be concerning with the specification of the component. So that specifications means it will be dealing with the dimensions. Each specification means it's a dimension. For example, if you are taking a connecting rod will be having a middle part will be having a shank. So the shank will be having an eye section. The eye section having a separate length and width of a flange. So that dimensions you will be having a design procedure, Rankine formulas that you will be using, and you will be checking for a strength, the required strength. So bending stress how much it can withstand. So once you are going for a design means you will be identifying the satisfactory dimensions. So whenever you are going for a design, you are going to check for the desired properties, and either the dimension is switched for that or not. That's what you have to check. So once you are going to identify that, then you are going to concentrate with the dimensions. So that dimension is what you are going to make for giving for the manufacturing. So once you are made in a manufacturing process, then you will be made the product for the your design procedure, whatever the design procedure for an individual component, then you are going to follow the design procedure. So from where you are starting the manufacturing is from the help of a drawing. So the drawing is what it is giving you your dimensions. So once you are making a product, then the product is able to easily replace whenever it is worn out. So that is what you will be saying as an interchangeability. So this interchangeability is what you have to fix some limits, fixed tolerances. That's what you are going to see about what is meant by a limit, what is meant by a fix, and what is a tolerance. Especially interchangeability, it is concerned with the tolerances. But a limits fix also important. It is also playing an important role. So based upon this limits and fix only, we will be going to make tolerances. As the next case, you are going to get a tolerances. So this is for a simplified example. What is the difference between a nominal size and actual size? So the actual size, if you are seeing that is being 3.5 inch and 1.5 inch of a respective length and width. Then if you are seeing the nominal size, that will be a rounded value with a 4 inch and 2 inch. That's what actual size of nominal size. We'll be going to see about what is nominal size. It is the size of the part specified in the drawing, and the basic size is the size of the part to which all limits of variations are determined. And the actual size, it is the size actual measured dimension of a part, and the nominal and basic size are often the same one. And seeing about the limit of sizes, you're going to make a manufacturing. So you'll be giving a specifications. For the specification, you got to give some tolerances. For the tolerances, you will be making a allowance for the case of two limits, maximum size and minimum size. You will be making an acceptance. That's what you will be saying as an upper limit and lower limit. So especially when coming to limits and fixed, you will be getting the component as under the short basis system and cold basis system. If it is coming into a fit, any components that is going to be get assembled means it is going to play this role only, short basis role and cold basis role. So in case of a design, we are going to get the short basis system as well as cold basis system. We are going to see what is the short basis system, cold basis system on the upcoming slides. So the limit now we are seeing. So there are two extreme possible sizes of a component. That's what you will be seeing, upper limit and lower limit. So the largest permissible size for a component is called an upper limit, and the smallest size is called a lower limit. So the deviation, if you are seeing, it is the algebraic difference between any given size and actual size. That is what said to be a deviation. You have seen in this sketch, you'll be able to get it. So this is what the line is actually is called a zero line. In the upcoming story, you are going to see it as zero line. That is not actually a basic size. So already you have seen what is the basic size, the actual size, and nominal size. So the basic size is what the required size, but we can't able to put it exactly to the basic size. But we can able to fix a tolerance. That is what you will be making a maximum size and minimum size. That's what you have seen about limits, upper limit and the lower limit. That's what upper limit is maximum size acceptable, and lower limit is minimum size acceptable. So you can able to make manufacturing of a shop within this range. This is what actually you can able to say this range as a tolerance. So that we are going to see on the upcoming slide. Now we are going to see about a deviation. So what is the meaning of deviation? The deviation means it is the algebraic difference between any given size and the actual size. So if you are seeing actual size is here, with respect to the actual size, we will be going to say the deviation. So the given size is maximum size means then we will be going to get upper deviation. Given size is minimum size means the difference with respect to the fixed size to the minimum size, the difference is what we are making a lower deviation. This is for the case of short basis system. And in case of short basis system, you will be making use of a small case letter, and in case of a whole basis system, you will be making use of a capital letters. So the actual deviation means it is the algebraic difference between actual size and the basic size. What is the difference between actual size and basic size? That's what you will be saying as an actual deviation. So seeing about a lower deviation, as already discussed, it is the algebraic difference between the minimum limit and basic size. So this is basic size. So this basic size, the minimum size is what this one. This is what a minimum limit or a lower limit. Okay. So this lower limit or minimum limit or the minimum size to basic size, what is the difference? That's what you are saying as a lower deviation. Similarly here, you will be seeing for the case of a whole system lower limit. So that is what the minimum size is here. Let's see, minimum size of pole is here, and the maximum size of pole is here. Because pole you will be knowing. For an example, if you are taking this as a 10.02 mm, that is the minimum size. Then you are enlarging the pole size to 10.022. You are enlarged it so that 10.92. So you are making increasing of 0.9 mm. So that means what you are enlarging the pole. That is the maximum size. So that is the maximum size you are enlarging the pole. So that is what in case of a pole, here you are taking minimum and here you are taking maximum. But short, so the inner one will be the minimum and the outer one is the maximum. So that is what in case of a shop. So here also you will be seeing. So this is the lower limit of pole to the basic size. So that is what a lower deviation here. And the maximum size for the pole is here. To this you will be having a difference. That is what the upper deviation. So upper deviation is what? It is the algebraic difference between the maximum limit and the basic size. The same thing, now you are seeing the basic size as a zero line. So it is a straight line corresponding to the basic size. So the basic size sometimes the diagram that it will be represented as a zero line. With respect to zero line, also you will be seeing what is the difference. So the deviations are measured from this line. That is from the zero line. With respect to zero line, you will be measuring the deviation. So you are able to see the sharp deviation and pole deviation. The same thing, whatever you were seeing in the previous slide, like that only, you will be getting the deviation for a lower sharp deviation and upper deviation. For a sharp and hole, you are going to say the same thing. See, for the case of a sharp, this is the minimum limiting size and the maximum limiting size. Now, if you are seeing maximum size to the zero line, maximum size is here. So that is what upper shaft deviation, and the minimum size of the shaft is here. So that difference is what this difference is what you are seeing as an upper shaft deviation, and from here minimum size to this zero line you will be saying as a lower shaft deviation. In the same way, you will be saying for the code. In the code, you can see the maximum minimum size is here to here. So from that to zero line, you will be saying that as an upper code deviation. And the minimum size of a pole is here. And from this to zero line, you will be saying this as a lower code deviation. And this zone is what actually you are saying as a tolerance. This is full tolerance. This is stop tolerance. This is what again you are going to see about tolerances in upcoming slide. So tolerance means what? It is a zone between the maximum and the minimum limiting size as shown in this figure. So you can able to see the tolerance for the case of short basis, tolerance zone, and then for the case of cold basis, the tolerance zone. That's what here you are seeing, cold basis, tolerance zone, and the short you will be having a tolerance zone. So you will be having the acceptable minimum size and maximum size. That is what you will be getting. Maximum size to minimum size difference. That is what maximum and minimum limit size. That zone is what you are seeing as an actually a tolerance zone. So the difference between the upper limit and minus lower limit. That's the difference is what you will be having a tolerance. That is what said to be as a tolerance. You are seeing a tolerance. This difference is what you are saying tolerance. Here also you can see the tolerance is maximum size and minimum size difference. You are saying as a tolerance. So fundamental deviation is what it is one of the two deviation which is conventionally chosen to define the position of the tolerance zone in relation to zero line. So in relation to zero line, so what is the position of tolerance zone? Where the position of tolerance zone is starting? That's what we will be saying as a fundamental deviation. And upper deviation, lower deviation, as already you have seen, what is the minimum size to the zero line to minimum size? The difference is what you are saying as lower deviation. Similarly, zero line to maximum size difference, you are saying as an upper deviation. As seen in the previous slide, the same concept will be seen for an deviation. So why we are getting all this deviation while making manufacturing? Because of the natural variability of the process. In manufacturing process, if you are involving, then you will be having a variation occurred in the sizes due to a natural conditions like variation in case of material, because material to material you will be having a precision is varying, ductile material as well as brittle material. The precision expectation will be a different. Aluminum you can able to expect more precision because of its missionability. But if you are going for a harder material like castagne and then still more harder material like titanium, then you have to select appropriate tool also for that. And depending upon that, depending upon the processing condition, machinability condition, you will be having a variation of accepted accuracy and expected accuracy. If you see, another thing is being what environmental fluctuations and vibrations, the human variability. Operator to operator also it will have a variation with the accuracy because more skilled operator can be able to produce a more tolerance and less skilled operator they can be able to make it the same condition of a machine. They will be producing a different result because of an inappropriate control. That is what a control is needed. It is an unavoidable process, but even though it is unavoidable process, it can be able to control by selecting the parameters properly, and by the way of controlling the parameters, it can be able to control. Anyway, you need to fix a tolerance. By fixing the tolerance, we can able to check either it is acceptable limit or a rejectable limit. Then you have to go for an review that we can decide after fixing the tolerances. That's what now you will be seeing about two main tolerances: unilateral tolerance as well as a bilateral tolerance. Whenever the tolerance is on one side of the basic size, it is said to be a unilateral tolerance. And if it is in both plus and minus, then it is what said to be a bilateral tolerance. You will be getting an example for this. So if you're seeing this sketch, first one is being what a unilateral tolerance. You can able to see only on the negative side you will be making accepting of the component. So 20 minus 0.004, but a plus you are not accepting. If suppose if you are trying to manufacture component and if you are getting the component as 20.001 mm, then the component is not accepted because it is not in the range of your tolerance. It exceeded the tolerance. But if it is being 19.002, then it is what? 19.002 means what is the accepted limit? The accepted limit means 19.996. 19.002 also not accepted. So if you are getting 19.997, 19.998, 19.999, the things are what accepted. So that is what you will be expecting. Only 20 minus 0.004 will be accepted. All the remaining thing, it is what? It is not accepted. So it is one-sided tolerance you are giving. But the same 0.004, you you are fixing on both sides. So previously, if you are accepting a 90.997, that 90.997 now it is not accepted. It is 90.9988 only it is accepted. But now 20.001 previously you had rejected, but 20.001 can be accepted. So that is what both sides 0.002 mm you are fixing. Even though the range is the same 0.004, at one side if it is going, you are rejecting it, but now you can accept it. So that is what a bilateral tolerance. So now coming into the fit, now you can able to see the difference. Here you are having a tolerance limit 1.500 in the case of pole, and the upper limit is being 1.502. And in case of a shaft, 1.493 and 1.495 is what upper limit, acceptable limit in case of a shaft. So there is a difference. In between there is a difference. That's what you will be having a allowance. So that allowance is what it is going to determine whether it is being a clearance fit or it is a transition fit or interference fit. Okay. So that's what the three main types of a fit. So now what is the meaning of a fit? So the degree of tightness. So depending upon this difference only, you will be either able to say either it is being having a looseness or tightness between the two manic parts. That's what especially we are having a soft basis and cold basis. Now the nature of fit is what it is characterized by the presence and size of a clearance and interference. So now we will be seeing the types of fits as I mentioned. So clearance fit, then interference fit, and the transition fit. We are going to see it detailing. So the thing clearance fit. So in this type of fit, the size of limiting for the case of an manic parts are so selected that clearance between them always occurs. So you can able to see here, you are always having a clearance. So you are having a tolerance zone of a hole and tolerance zone of a shaft, and you will be getting a clearance. Here the clearance is existing. You are having a minimum clearance, a maximum clearance. So you are always having a clearance. So if you are noticing here, the tolerance zone of the hole is entirely above the tolerance zone of the shaft. If you are seeing the tolerance zone of a hole, this is the tolerance zone of a hole. So this red diagonal one, this is the tolerance zone of a hole, and similarly this is the tolerance hole of a shaft. So tolerance zone of the hole is what? As you say, entirely above the tolerance zone of the shaft. So that's what you will be saying. The tolerance zone is what of the hole is always above the tolerance hole of a shaft. So that's what you are having in case of a clearance fit, and also about maximum clearance and minimum clearance. So in a clearance fit, the difference between the minimum size of the hole and the maximum size of the shaft is known as minimum clearance. If you are seeing the minimum clearance, the minimum size of the hole, the hole minimum size is here. The hole minimum size is here. So the minimum size of the hole and the maximum size of the shaft. So here maximum size of shaft and here minimum size of the hole. This is what you are getting a minimum clearance. And you can able to make the maximum clearance as this is what the maximum size of the hole. The maximum size of the hole is here and the minimum size of shaft is here. That difference is what you will be saying as a maximum clearance. Because this is what the maximum possibility you can manufacture. So that much of maximum clearance you can get. And this is the least possibility you can be able to get. So this is the minimum clearance you can get in case of a clearance fit. So the clearance fit that can be said with other name as slide fit, easy sliding fit, and running fit, because you have the clearance. So you can be able to easily slide the shaft inside the hole. So easily you can be able to make movement. That is what it is not required to give tons of pressure. Simply by means of your hand pressure itself, you can be able to insert it. If it is being just a clearance level of it, you can easily run it. So that's why you are saying it as a running fit or a easy sliding fit or slide fit. But coming to the next case is what it is being interference fit. So here the case will be different. So you are going to make the type of fit, the size of limiting for the manic parts are so selected. Interference is always occurring. You are not having clearance, but instead you will be having interference, getting interference. So what is happening? Previously you were seeing the tolerance zone of a hole, it is getting always above the tolerance zone of a shaft. Now we are going to get a tolerance zone of a hole, it is getting below the tolerance zone of the shaft. So that's what you will be seeing. Tolerance zone of the pole is entirely below the tolerance zone of the shaft. And also the interference is occurring. So here also you will be saying what will be the maximum interference, what will be the minimum interference. So the case the interference, minimum interference and maximum interference. The minimum interference will be what? You will be having the maximum size of pole here, and minimum size of shaft here. That difference is what you will be saying as a minimum interference. Similarly, the maximum interference, the maximum size of pole to minimum size of the maximum size of pole to the minimum size of shaft. That is what it is going to give you as a maximum interference. So maximum size of shaft is here, and minimum size of pole is here. Okay. The minimum size of pole here and the maximum size of shaft is here. That difference is what you will be making as a maximum interference. So here you are required to give a press fit. That's what you will be saying a shrink fit, heavy drive fit, light drive fit. Otherwise, it can also say it as a press fit because you are required to give a tons of loads to make a fitting. So that's why you will be making other names: shrink fit, heavy drive fit, light drive fit, and sometimes press fit also. But the third type of a category, that is a transition fit, if you are seeing. So here you will be selecting the matrix parts in such a way that clearance or interference may occur depending on the actual size of the matrix parts. So if you see, it may be noted there will be a overlapping. So there will be a overlapping of tolerances. Previously, you had given a reference that either the pole tolerance zone is above the shaft tolerance zone and pole tolerance is below the shaft tolerance zone. Now, if the zone is not getting a difference, it is having a overlapping. So with the tolerance zone of a pole, the tolerance zone of a shaft is going to get overlap. That is what the case of a transition fit. So the transition fit may be a force fit or a tight fit and a push fit. So now coming to the basis of a limit system, a pole basis system and a shaft basis system. You say about a pole basis system, name itself it implies you are giving importance to pole. So you are not going to make a variations to pole. Pole you are going to keep as a constant member. Only thing you are going to make variation is what on the shaft faces. So then the type of a limit system is what you will be saying as a pole basis system. So that's what you can able to see. Pole you are making as a fixed one. Only you are making variation in case of a shaft faces. So that you will be having a clearance. So this one is what clearance fit, and two you will be having overlapping. So that is what it is either a clearance or a interference. It is a transition between the two. So interference means it is getting interfering. Tolerance is getting interfering. So that is what the shaft is getting above the tolerance zone of the pole. So that's what you will be saying a interference fit. So the same way, shaft based system, you will be keeping the shaft as a constant member, so that the difference will be obtained by varying the pole size. So you can see the pole size is getting varied, so that you will be getting a clearance here, that is clearance fit, and here you will be getting overlapping of a tolerance zone. So that is what a transition fit. Here you are getting interference. It is interfering as it is what it is required to give a press fit and tight fit. Okay, so that it is what it is called to be as a type of category interference fit. For this fit system, you will be having an Indian standard system for limits and fits. So according to the Indian standard IS 919 part 1993, the system of limits and fits comprises 18 grades of fundamental tolerance. That's what you will be having a grades of accuracy of manufacture and 25 types of fundamental deviations indicated by letter symbols for both poles and shaft. And for a pole, we will be using capital letter A to capital letter Z for the poles, and the small letter will be used for the case of shaft, A to Z, but it is small case letter. So the diameters will be ranging from 1 mm to 500 mm. Unilateral pole basis system is what it is recommended, but if necessary, you can consider bilateral. Unilateral or bilateral basis system may also be used. The 18 tolerance grade are designated as IT01, IT0, and IT1 to IT16. These are all what called to be as standard tolerances. So the standard tolerances for a grade IT5 to IT7 are determined in terms of a standard tolerance unit in microns, where this standard tolerance unit I can be identified using this empirical relation 0.45 cube root of D plus 0.001 D, where D value is in geometric mean diameter in mm. So as it being mm, as you are multiplying with 0.001, it will be converted into microns. So the following table, it is what showing IT5 to IT16, what will be the magnitude, how to calculate the magnitude. So the relative magnitude for the tolerance gate, because in the drawing you can able to get a tolerance grade value. With the help of a grade value, you can able to identify what will be the tolerance. So if you are getting, for an example, IT7 means that will be 69. So I formula you are having, already you are having a correlation, empirical relation is there. So under you can substitute and you can identify what is the magnitude for the tolerance grade of IT7. Any IT, what is the tolerance grade that will be given in the specification. So based on that, you can able to identify. So one example problem also you can see so that you can understand this concept. So the value of standard tolerances for grade IT01, IT0, IT1 will be identified using this empirical relation. For IT01, 0.32, 0.3 plus 0.008D, and IT0, 0.5 plus 0.012D, and for IT1, 0.8 plus 0.02D. So where D is the size of a geometric mean diameter in mm, and the tolerance of grade IT2 up to IT4 are scaled approximately geometrically between IT1 to IT5. Similarly, the fundamental tolerances of grade IT01, IT0, IT1 to IT16 for a diameter scale ranging from 1 to 500 mm will be given in the table 2. So that is what 1 to 500 mm. So diameter is over 1 mm to 3 mm, 3 mm to 6 mm, like that the steps, and it is going up to 500 mm. So up to 500 mm, you will be having IT grade 01 to up to IT16. That is not a IS, Indian standard system, standard specified. So it's an Indian standard system. From this, you will be having the IT grade value. So from this, you can be able to make taking up on a value. What is the I value? Okay, the standard tolerance grade value. And also you can make use of an empirical relation formula for identification of diameter. So we have already discussed for the pole there will be upper deviation, capital ES, capital E. Similarly for a short basis, small es, small e. So for the case of short, you will be having small es and lower deviation is small ea. So according to Indian standard, for each letter symbol, the magnitude and sign for the two deviations can be identified with fundamental deviation. That is getting formulated in case of table 3. So we will be having a microns, how to make a calculation, and for B value greater than 120, what you have to take, and less than 120, what you have to take. That is the shaft designation will be given. For that, the formula, what is the respective formula you can take? Okay, that is what you will be having a formula for fundamental shaft deviation. So now considering a simple problem, a dimension of the two mating force according to basis of the pole system are given as follows. Pole having a limit 25 mm and shaft having 24.97 mm. This is one limit. Another limit is given. Upper limit is given for a pole. It is 25.02 mm and lower limit 25 mm, and for a shaft 24.97 upper limit and lower limit is being 24.95 mm. So now we are required to identify what is the pole tolerance and the shaft tolerance and what is the allowance. Now, for the case of this problem, we are writing a given data. What is the lower limit of lower limit is being 25 mm and the upper limit is 25.02 mm because you enlarge the pole. That is what 25.02 is the upper limit. But the shaft, whichever is the maximum size, that you will take as an upper limit. So you will be having 24.97 mm is the upper limit of shaft, and lower limit of shaft is being 24.95 mm. This one important. Whichever the maximum size, that you can take upper limit for a shaft, but in a hole, whichever is the low value, that low value is what you will be getting 25 mm as the lower limit, and the upper limit is being 25.02 mm. So now the hole tolerance, we know the hole tolerance, that will be what upper limit of hole minus lower limit of hole. So the upper limit is what 25.02 mm minus 25 mm. So you are getting a hole tolerance of 0.02 mm. But here shaft is what 97 minus 95, the same 0.02 you are going to get. So upper limit of shaft minus lower limit of shaft, that is being 24.97 minus 24.95, so same 0.02 mm. So for a pole, you are having this tolerance, and the shaft, you are having this tolerance. And allowance means you will be having the lower limit of pole minus upper limit of shaft. So lower limit of pole is for 25 mm and upper limit of shaft is 24.97 mm. So that allowance range is 0.03 mm. Now we will see one more problem that is showing you how to make use of tables. So as we have seen, there is a IT tolerance grade. You can be able to see the indication like this in the problem. So designation 40 is for the diameter of the shaft, 40 mm diameter, and you will be going to consider tolerances with the microns level. For that IT grade value, you are going to get for an whole basis system because capital letter, and here you will be seeing small case letter. So this is short basis system, IT grade value of 7, and here IT grade value of 8. So now you will be making the shaft designation 40H8 and F7 for pole. So that is what you are identifying. Pole is having IT8 and shaft is having IT7. And the basic size is being 40 mm. And if you have seen basic size 40 mm, in the table there will be a range 30 to 50 mm one range is there. So in this within that range it is going to lie. So you can able to see 30 to 40 mm diameter over 30 to 40 mm diameter and 40 to 50 mm diameter it is going to lie. Okay. So from this, with the help of this, we are going to identify what will be the required diameter. And you are also having a formula. D equals square root of 30 into 50. So that will be a 38.73. So for a 30 to 40. So 30 to 40 is here. Okay. On that, you will be having the pole basis system. This is for a pole basis system. And pole basis system will be having SA. And even you can see here 39 mm. So you'll be getting a 39 mm. That is what by formula also if you are using, you are going to get 38.73 mm. And while you are solving the problem, you are seeing that the range is being 40 mm, and by formula you can identify 38.73, and the table value also there. But for identification of standard tolerance units, the micron values, you are having the another empirical relation, and if you are substituting that empirical relation, this calculated value 38.73, you will be getting that I value as 0.00156 mm, that is 1.56 micron. That is what you will be getting in mm means 0.00156, because the micron to mm, if you have to convert, you have to multiply by 0.001 mm, because the micron means 1 by thousands of an mm is what micron. That's why you are multiplying by 0.001 for getting conversion into micron to mm. So now you have found 0.00156. So that 0.00156 you are going to multiply with the top on a table. As you have seen, this table is what you will be having an IT grade of 8, okay, and IT grade of 7 for the case of pole basis system. So that's what you will be making IT grade of 8 for the case of pole basis system, IT grade of 7 for the case of a short basis system. So from that you will be having an identification of the microns value 25I and 69. So I value you have already calculated. That calculated value will be multiplying, and you are identifying what is the standard tolerance for the pole and what is the standard tolerance for the case of shaft. So now fundamental deviation you can identify as you are knowing this value of an standard tolerance for the case of pole and shaft. So now from with respect to this table you will be identifying. So what will be for the case of a shaft? Values being this 5.5 D into 0.41. So that's what it is available at this table. So 5.5 into 0.41. Okay, that is available in the table formulas for our designation of F. So here you are having a designation of F. So after designation of F, you can able to see there will be a 5.5 D and power 0.41. So by making use of this calculation, you can be able to identify what will be the fundamental deviation. For an upper deviation, you can be able to identify upper deviation. Similarly, a lower deviation is there. So you can be able to calculate what is the deviation. Okay. So fundamental deviations for a shaft, it is calculated. It is being ES minus IT. Okay. So you can be able to identify that. Okay. So you can be identifying what is the fundamental deviation for upper deviation of shaft and lower deviation of shaft. Stay to the letter. Okay. And the negative signs, that is what indicating the fundamental deviation is lying below the zero line. And now identification of limit of sizes. We know the lower limit for the hole is being 40 mm. That is what the basic size. And the upper limit of hole, it is being lower limit of hole plus tolerance. So that you will be identified the tolerance for hole as already 0.039 mm. So adding it and you are getting the answer as 40.039 mm. About upper limit of shaft, lower limit of hole or basic size minus fundamental deviation. Because the shaft F lies below the zero line. So that you are already identified fundamental deviation as 0.025 mm. So from the basic size of 40, you are subtracting that, so that you are going to get upper limit of shaft. So the lower limit for the shaft, that is upper limit of shaft minus tolerance for shaft. So you are making upper limit is being 39.97 mm minus 0.025, you are getting 39.95 mm. So it's all about this limits with tolerances. This is what in the second model we have seen. So the next model is about third model is with the design of a cylinder piston. We will see it on the next video class.